Let's play the Impossible Sudoku. This website claims to have the Impossible Sudoku. It has been mathematically proven that the minimum number of clues necessary to solve a Sudoku puzzle is 17. This is one of those minimum Sudokus. At the bottom of the page, he bets no one can solve his Impossible Sudoku. That's like waving a red flag in front of a bull. What do you say we give this one a shot? First, I constructed a template. Every box contains all possible solutions from 1 through 9. For those of you who have played Sudoku, you may have experienced the thrill of victory, only to notice that something wasn't right. You notice duplicate numbers in a row, column, or grid. That's when your heart sank and you realized that you had made a mistake. The exclamation points that you see at the end of each row, at the bottom of each column, and in the shaded area called the grid tracker will disappear when the sum of the digits for that row, column, or grid equal 45. When all the exclamation points have disappeared, you have won. I also provided an additional feature in the green shaded area called row, column, grid that you can use to keep track of where you left off should you get sidetracked. If you would like to have a copy of this Excel workbook, simply email me at neo, that's N-E-O, at theskepticarena.com, and I will send you a copy. The first tab of the book contains instructions, tips, and a link to websudoku.com, where you can find puzzles in 4 categories: easy, medium, hard, and evil. The second tab of the book contains this template. The third tab is called Play. This is where you will copy the given numbers into a copy of the template. Advice: never touch the template on the second tab, except to copy it to the Play tab. The first thing we have to do is to copy the given puzzle into our template on the Play tab. I then change those numbers to red font so that I will always have the original puzzle while I play. Now we are ready to begin. The first step is to use the given numbers to remove duplicates from the rows, columns, and grids. You could go box by box. For instance, starting with the top leftmost box, B2, you would remove any given numbers that appear in row 1, column 1, and grid 1. So you would remove a 1, a 2, a 5, and an 8. Then you would repeat that process for all unsolved boxes. In this case, 63 more boxes. I prefer a faster method, which I also find less prone to error. I remove all of the duplicates from row 1, in this case a 1 and a 5, by deleting them from the first unsolved box, copying the result, and then pasting that result in the remaining unsolved boxes in row 1. Let me demonstrate. I go to the first unsolved box and remove the 1 and the 5 that are given in row 1. I then copy that result and paste it into the rest of the unsolved boxes in row 1. Then I repeat that process for all 9 rows. However, I cannot use this time-saving trick on the columns and grids because the rows have different numbers in them, which would cause me to overwrite boxes with incorrect data. So when the 9 rows are finished, I move to column 1 and remove the 1 and the 8 from all boxes in that column. Then I do the same for the rest of the columns. Finally, I repeat the process of removing given numbers from all 9 grids. After removing all of the duplicates of the 17 given numbers, here is the result. Since there are now fewer numbers in the unsolved boxes, I was able to make this easier to see by enlarging the font. Notice box J3. That box has been solved. It is the only box that we solved. This is our first clue that this puzzle is going to be really difficult. Usually you get more than one solved box. The reason I marked it with an underline is because I need to remove duplicate 7s from the same row, column, and grid, but I didn't want to do it when I was in the middle of my algorithm. Now that we are done removing duplicates from the given numbers, we remove the duplicates created when we solved the 7. And here is the result. Notice the pair in boxes K3 and L3. That tells us that there must be a 3 in one of those boxes and a 9 in the other. Even though we don't know which box contains which number, we can still use that information to delete other 3s and 9s in the same row and grid. Since the 3 and 9 are in different columns and we don't know which number is in which column, we can't delete any 3s or 9s from either column. Let me just take a minute to interrupt this puzzle so I can give you an example from a different puzzle that shows you how to take advantage of triplets. In the upper right grid we have a 5, an 8, and a 9 distributed in 3 boxes. Therefore, we can remove any 5, 8, or 9 that appears in the grid. That information will enable us to solve 3 boxes in that grid. Since the triplet is spread across different rows and columns, we cannot use that information in the rows or columns. In the bottom center grid, we have a 2, a 7, and an 8. Because the triplet boxes are also in the same column, we can eliminate duplicates of those numbers in the column as well as the grid. Now, getting back to the Impossible Sudoku. Let's look at the results after we use the information in the 3-9 pair boxes. We've solved 2 additional boxes. They have been underlined so that we can go back and eliminate any duplicates created by those solved boxes in the appropriate rows, columns, and grids. When finished, we remove the underlines and view the results. Now we scan the rows and columns again. This time we are searching for unique numbers, which are numbers that only appear once in a row or column. Finding a unique number solves that box. At the same time, we also search the rows and columns for numbers that must appear in a particular grid, and therefore cannot appear anywhere else in that same row or column. We will call these numbers particular numbers. Finally, we search the grids for unique and particular numbers. Particular numbers in a grid will appear in the same row or column, allowing us to delete any duplicates that appear in the other 2 grids in that same row or column. If you'll look at the first grid on the bottom row, you will notice that a 3 appears in only one box. Therefore, the 3 is a unique number, and that box must be a 3. After solving for the 3, we now have 2 7s that appear in the last column of the grid, but nowhere else in the grid. Therefore, one of those 2 boxes must be a 7. That means that we can remove any 7s that appear in that column in the grids above. Those 7s were particular numbers. Now we'll look at the results of our search to find unique numbers and particular numbers. Now you see why I selected that box. It contained the only unique number in the entire puzzle. The 4 7s we removed from the last column above the grid were also the only particular numbers which we were able to remove. For all our efforts, we have only solved 4 boxes in addition to the original 17 that we were given. If this were a baseball game and we were running the bases, 21 boxes out of 81 would mean that we are standing on first base. And the bad news is we've reached the end of our rope. On his website, the guy did provide a link to the solution to this puzzle. From perusing his site, I got the impression that he is a computer programmer, which leads me to believe that he solved it by using a brute force computer algorithm. Computers can use such algorithms to solve difficult problems in seconds, but using brute force methods are impractical for humans. You could be sitting here for weeks trying all the different permutations. So we must rely on our resourcefulness. What we must do is study the possible solutions and choose the most promising path, or in other words, guess. But it will be an educated guess. We want to look for boxes that have been reduced to only 2 possibilities. If we guess wrong, we simply go back and follow the other number which we now know is correct. There are 5 boxes that fit our criteria. If you examine the 2 boxes with the 3-9 combination and then project how many boxes you can solve by choosing either number, you will see that those boxes will get us nowhere. I'll save you some time by telling you that J10 and B3 also fail to solve very many boxes. But F3 was much more promising, especially if I choose the 5. So we insert a new worksheet, give it the name of the box we are guessing, and then copy the puzzle from the tab where we got stuck to the new tab. This way, if our guess fails, we simply recopy the puzzle from the tab where we got stuck and begin again, only this time using the correct number. Let's play this hunch so you can get a feel for how to use this template. When you run out of solved boxes to follow up on, then you must search the rows, columns, and grids for pairs, triplets, and unique and particular numbers. These will create more solved boxes for you to eliminate. For example, in row 11, this 1 is the only one that appears in the entire row. That unique number can be solved. The bottom row only has one box with a 1. That box is now solved. In the bottom row, the boxes containing 25, 29, and 259 form a triplet. So you can remove any 2s, 5s, or 9s that you find in that row. So, what was the result of our guess? Well, keep your eyes on the exclamation points. We have solved the Impossible Sudoku. We played and beat the Impossible Sudoku. Now we're going to play one that is even harder. You might remember that we were able to solve the Impossible Sudoku by making a strategic guess that paid off for us. The first time I played this puzzle, it took me 6 guesses to solve it. So I played it again using a different path, and it still took 6 guesses. Then I carelessly deleted the solution and had to solve it all over again from scratch. But this time I chose a different path and was rewarded by solving it in only 4 guesses. Using this new path as a basis, I then experimented with a different guess, playing it one last time in an attempt to solve it in fewer than 4 guesses. This puzzle was not a minimum Sudoku, which only gives you 17 clues. It provided 24 starting clues. After removing all duplicates and finding the unique numbers, here's the result. We've solved 7 more boxes, so now we only have 50 more to go. Unfortunately, we are out of tricks and must guess our next move. I chose the 4 in box D3 and took it as far as it would go before getting stuck again. For my next guess, I chose the 7 in box F6 and played that path until it too ran into a dead end. My third guess was the 9 in K7. Remember, I was trying to beat my best effort, which required 4 guesses, so this path had to lead to victory or else. Just as I could almost taste the thrill of victory, I ended up in this situation. It looked like I was going to have to resign myself to making that 4th guess. Then I realized that I did not have to guess. I could use logic to solve the puzzle. When you encounter a square like this one, no matter which number you choose for the upper left box of the square, you will solve the puzzle. That is because this is one of those rare Sudoku puzzles with 2 solutions. In each row, column, and grid, it doesn't matter in which order you put the 6 and the 7. They will sum to 13. Therefore, we win either way. Keep your eyes on the exclamation points as we solve the puzzle. If anyone out there can solve this puzzle in less than 3 guesses, please email the answer to me at neo@theskepticarena.com.